At first glance, an MRI just looks like a giant donut. It actually is used for creating detailed three-dimensional images of the body. So, what is an MRI and what is it used for? MRI stands for magnetic resonance imaging. It is a non-invasive technique known for its ability to produce detailed, three-dimensional images of soft tissues, including organs, muscles, bones, and blood vessels. It is used to detect disease, diagnose conditions, and monitor treatment. Specialty MRIs image complex parts of the body including the heart, spinal cord, brain, joints, etc. Here are a few examples. A cardiac MRI, CMRI, images the overall structure of the heart including the thickness of the walls of the heart. Since the heart is so dense, it is difficult to image this with a standard MRI. Spinal cord MRIs are used to detect issues such as cerebral vessel, aneurysms, eye and inner ear conditions and spinal cord conditions. Functional MRIs show the anatomy of the brain and their functions. Magnetic resonance angiography image blood vessels and flow of blood in the body. These detect issues such as blockage or narrowing in the blood vessels. So how do MRIs work? An MRI machine uses a powerful magnet to create a strong magnetic field around the patient, aligning the hydrogen-proton molecules in their bodies. After the protons are tipped out of alignment, they emit energy that the MRI machine detects and the computer reconstructs them into a three-dimensional image. Water molecules are abundant in the body, which makes hydrogen protons ideal for producing detailed images of our tissues. Let's dive into how this all works. First of all, why are hydrogen molecules useful in this process? Hydrogens are abundant in water and fat, which is abundant in the human body. Hydrogen consists of only one proton, one electron and 0 neutrons. The atomic nucleus has a property called nuclear spin, meaning that both neutrons and protons spin about their axis. The nuclear spin is quantized, meaning it can only exist in discrete energy levels. Its orientation in a magnetic field is described by the magnetic quantum number. When a proton and a neutron pair in the same energy state, their spins are opposite, 1 plus a half, 1 minus 1 half. So the total spin cancels out and they do not contribute to the nucleus's magnetism. Since the hydrogen atom is unpaired and doesn't have a neutron, the spin cannot be cancelled and the proton acts like a magnet. Individual unpaired atomic particles, like in hydrogen, each have a spin of 1/2, which is known as the spin quantum number. The spin quantum number determines how protons align in the magnetic field in response to a radio frequency pulse. In a magnetic field, slightly more protons have an upspin or slightly more protons have downspin, creating a net magnetization. What is net magnetization? It describes the overall magnetic effect of many protons. Since the hydrogen nucleus only has one proton that possesses a net spinning charge, it acts like a magnet. The nuclei act as magnets with north and south poles, which are called magnetic dipoles. The magnetic dipoles, without an external field, are randomly positioned. When the static magnetic field is applied, the protons align with that field. What is a static magnetic field? Static magnetic fields are created by magnets or charges that move at a steady flow, such as in direct current electricity. Static magnetic fields are used by MRIs to align the protons in the body before they are knocked out of alignment by a radio frequency pulse. What happens when you apply a radio frequency pulse? When a static magnetic field is applied, protons align in two ways. Protons can align either in the same direction as the magnetic field, which is the lower energy state and is called spin up, plus a half, or in the opposite direction, which is the higher energy state and is called spin down, minus a half. Protons can switch between these two states by absorbing more energy to spin down, or release energy and spin up. Where does the proton get energy? When the MRI machine sends in a radio frequency, RF, pulse of energy, the protons absorb the energy and jump from a low energy to a high energy. This absorption of energy by a proton is called resonance. When the RF is turned off, the protons relax back to a low energy state, aligning back with the static magnetic field, and in the process, releases radio frequency waves which are detected by the MRI scanner to create the image. The MRI can only create the image when the RF pulse matches the Lama frequency for hydrogen. This is calculated by this crazy mathematical equation that we are not about to dive into. So what is the Lama frequency? When hydrogen protons are placed in a strong magnetic field, they wobble in a circular motion called precession. The speed of this wobble around the magnetic field is called the Lama frequency. This frequency is directly proportional to the strength of the magnetic field and determines the exact radio frequency needed to excite the protons. The Lama frequency used for magnetic resonance imaging ranges from 1.5 to 3 Tesla, which is 1,000 to 50,000 times the Earth's magnetic field. But wait, if the MRI magnetic field is stronger than the Earth's magnetic field, why doesn't it affect the Earth's magnetic field? Actually, this has a very simple answer. Although an MRI's magnetic field is much stronger than Earth's, it is confined to a small area and drops off quickly with distance, so it has no meaningful effect on Earth's large-scale magnetic field. Why are radio waves used? Radio waves are used because they can be adjusted to match the proton's Lama frequency. When the radio frequency pulse is applied, radio waves give the protons just the correct amount of energy to tip them out of alignment with the static magnetic field. So how does the MRI produce images of the body? The MRI sends out a RF pulse that matches the static magnetic field that the patient was placed under. When these protons are tipped out of their orientation, they wobble together in a synchronized manner, called precessing, producing a signal the MRI can detect. The MRI has 3 electromagnetic gradient coils that create magnetic fields in different directions, X, Y, and Z. Where these fields intersect is called a voxel. Voxels are a part of a grid on the MRI that divides the image by section and determines the image's resolution. When the RF pulses, the short radio waves, are turned off, and the protons relax back to a low-energy state to their original alignment, 2 events occur simultaneously. During this relaxation process, the protons release the energy they had absorbed from the RF pulse. The energy that is released is transferred to the surrounding molecules, lattice. T1 relaxation is the time it takes for this energy to be transferred into the lattice, while T2 relaxation measures how fast the energy in the lattice decays. An MRI technician will send out 2 RF pulses. The first pulse focuses on T1 relaxation. After this first pulse, they allow the tissues to recover back to their original orientation in the static magnetic field. These T1 images are used to show autonomy. The second pulse focuses on T2 relaxation. These images are used to look for abnormalities in the body. These images are often called water images because diseased tissues that are inflamed or tumorous contain more water. Water slows down the decay of energy in the lattice. These signals don't immediately create an image. Instead, they are stored in a K-space, which is a digital map containing all the information on how to build the image. The Fourier transform, a mathematical process, turns K-space into the final image. Okay, that was a lot. Let's briefly review how MRIs create an image. First, the patient is placed under static magnetic field, making protons found in water to line up along the Z-axis. Then, a radio frequency pulse is applied at the Lama frequency matching the static magnetic field. The RF pulse excites protons, tipping them into the XY plane. Then, gradient coils locate the signal in 3D space. When RF pulse stops, protons relax and release energy. Signals are stored into a K-space and the Fourier transform converts them into the final image. The MRI seems really complicated. How did they come up with such an intricate machine? Before MRIs were invented, X-rays, fluoroscopy, ultrasound, positron emission tomography, and computed tomography were used. To avoid using ionizing radiation, MRIs were a big step forward in medical imaging. The concept of quantum spin was developed by Samuel Goudsmit and George Uhlenbeck in 1926 to explain atomic spectra, light emitted or absorbed when electrons move between energy levels. In an emission spectrum, electrons fall to lower levels and release energy as light photons. In an absorption spectrum, atoms absorb specific wavelengths, causing electrons to jump to higher energy levels. These energy changes are quantized, meaning they occur in fixed steps. With the question of why electrons are so limited in energy levels and can only move in discrete steps, Wolfgang Pauli brought the idea of spin quantum theory with his famous exclusion principle, so famous, I didn't know about it before chemistry class. The Pauli exclusion principle explains how electrons are arranged in atoms and why they don't all collapse into the lowest energy level. It states that no 2 electrons can share the same set of quantum numbers. In orbitals, electrons pair with opposite spins, plus a half and minus a half, which helps keep them stable and distributed across energy levels. The idea was confirmed by Otto Stern and Walter Gerlach, whose Stern-Gerlach experiment showed that a beam of silver atoms splits into 2 in a magnetic field, proving magnetic moments are quantized and providing the first evidence of electron spin. Isidore Isaac Rabi used molecular beam experiments with a weak, non-uniform magnetic field to study nuclear spin. The field split particle beams without disturbing energy levels, allowing him to measure the spins of alkali nuclei and the proton from their deflection patterns. In 1937, Isidore Isaac Rabi showed that nuclei can flip their magnetic orientation when exposed to the right radio frequency, absorbing and re-emitting energy. By modifying his molecular beam setup, he observed resonance, allowing atoms and molecules to be identified. In 1946, Edward Proussel and Felix Bloch both found a way to study the magnetic resonance of atoms and molecules in solids and liquids, allowing this information to be used in the invention of the MRI. They came up with the idea to use magnets to take pictures of a living being with nuclear magnetic resonance spectroscopy. In 1971, Damadian wrote about the difference of proton relaxation, as T1 and T2, among normal tissues and cancerous tissues, and proposed the idea of external nuclear magnetic resonance imaging. Paul Lauterbur advanced NMR by producing the first cross-sectional images, while Raymond Damadian proposed using it to detect tumors. Damadian and his team later created the first whole-body MRI images. But how did the MRI affect the science of today? Over the last couple of years, the MRI has been developed through collecting more data, improving image reconstruction and hardware systems. Progress has used new technology from outside of the MRI field, including computer science, data processing and semiconductors. MRIs can now be very detailed and have given the MRI additional abilities. MRI machines use extremely strong, stable magnets, typically up to 3 Tesla. They rely on superconducting magnets, which have no electrical resistance when cooled to cryogenic temperatures using liquid helium, which is around 4.2 Kelvin or -269 Celsius. Now, the world's most advanced magnets can surpass 25 Tesla, which is 500,000 times stronger than the Earth's magnetic field. These superconducting magnets that are used in MRI machines, particle accelerators and now magnetic levitation trains. Tongkang Li is developing atomic-scale nuclear magnetic resonance to observe single molecules and atoms. His team combines NMR with carbon-13 isotopes and two-dimensional materials to study tiny structures, potentially revealing the exact atomic makeup of proteins, DNA, and drugs. What does the future of MRIs look like? Artificial intelligence is speeding up and improving disease diagnosis by analyzing large datasets and detecting early abnormalities, making data science an essential skill for radiologists. Portable MRIs are now more common, allowing scans to be done at a patient's bedside instead of moving them to a traditional MRI machine. With researchers beginning to understand the impact of helium and energy usage, manufacturers are making an effort to reduce their environmental impact, and designs that are helium-free and energy efficient are being produced. In 2025, MRI designs prioritize patient comfort with wider bore or open MRI machines and Philips Comfortone system, which reduces noise by about 80%. MRIs for children sometimes also are paired with VR headsets and soft lighting to make the patient feel more at ease. What are the benefits to using MRIs? First, MRIs are a non-invasive technique that doesn't involve exposure to radiation. It is able to image the soft tissue structures of the body and is able to identify a broad range of disease and conditions. It is valuable because it is able to detect abnormalities that are unclear in other imaging methods. Gadolinium, a metal used as an MRI contrast agent, is safely bound to a chelating agent and injected into the bloodstream to highlight structures. This contrast agent is less likely to cause an allergic reaction than contrast agents used in X-rays or CT scans. The kidneys are also able to excrete it through the urine. They are also able to monitor pregnancy safety. What are the drawbacks to using MRIs? And what are some solutions to these problems? A strong magnetic field is dangerous when patients have implanted medical devices. Medical devices may malfunction or distort the image. To avoid this, thorough screening questionnaire before MRI is necessary, though some can be scanned under strict conditions. Otherwise, alternative imaging such as CT scans are available. Slight risk of allergic reaction in using contrast materials such as gadolinium. Physicians should review patients' past medical history. Non-contrast MRI is used when possible. Gradient magnetic fields produce significant noise exceeding 100 decibels, which can damage hearing. As of now, headphones are provided during the procedure, but newer machines that are a lot quieter are replacing noisy machines. Tattoos may heat up during the procedure due to the metal in the ink. To avoid this, tattoos under 6 months must have a rescheduled MRI. Older tattoos have ice pads or padding is placed over them to avoid overheating. Patients who are unable to remain still or follow breathing instructions require special attention. Using sedation or immobilization aids can be used to help with this. Individuals with high body mass index may not fit into standard MRI scanners. To accommodate these people, wide-bore or open MRI scanners can be used. Those with claustrophobia may not feel comfortable using the MRI. This can be solved by using an open MRI scanner or mild sedation where necessary. Now that we've focused on the drawbacks to the human body, we also should consider the effects MRIs have on the environment. Radiology contributes about 1% of global greenhouse gas emissions, with MRI machines being major energy consumers. Hospitals, which use roughly twice the power of typical commercial buildings, can significantly reduce emissions by turning off MRI systems when they are not in use overnight. This practice could lower MRI energy consumption by 25 to 33%, saving approximately $1,717 to $2,943 per machine annually, while also reducing overall carbon footprints. Gadolinium, used in MRIs, can be toxic when exposed to UV light. It enters the environment through urine and wastewater, as treatment plants cannot remove it. This suggests a need for implementing a removal technology for gadolinium either in the wastewater treatment plants or collection of this urine in waste containment. Medical technologies like MRI raise ethical questions, including concerns about overstepping divine mysteries, though Christians believe God's ways are beyond full human understanding, Isaiah chapter 55 verses 8 to 9. While we should seek to learn about God, we must do so with humility and respect. Christians see medical advancements as gifts that help care for the body, which is described as a temple of the Holy Spirit, as said in 1 Corinthians chapter 6 verse 19, and as ways to explore God's design. However, ethical issues remain. Unnecessary MRI use can waste resources, patient privacy must be protected, and sensitive diagnoses may lead the patient to desire to undergo euthanasia. Initially, the sheer complexity of MRI technology felt overwhelming as everything I read from every source gave me more questions and more answers. Even with the research that I have done, radiologists have 8 years of study and 5 years of residency to complete their education in operating and diagnostic imaging. I found it really interesting how all three sciences sectors came together to solve real-world problems. There you have it. MRI technology does indeed combine principles of physics, chemistry, and technology to create such a detailed picture of what it looks like inside us.